Hi everyone, Elliot Jacobson here for Disaster Diaries. It is October 6th, 2021, and we are making it through another month here with a lot of things going on worldwide, including record rains in Italy, close to 30 inches in a 24-hour period. But that's not what I want to talk about today. What I want to share with you is a little bit of research I have done on methane using some publicly available data, and to kind of talk about why I think this is the right way to look at the data and just what a serious problem it points to. I'm surprised that this is not getting more direct mention by climate scientists, but this is really what terrifies me, honestly. And I'm going to just start right now with kind of why I'm making this video, which is a tweet that I posted that apparently got some feedback. People didn't fully kind of understand what I was doing, and I just want to explain it to you. So I made this tweet right here where I say June 2021 saw the largest annual global methane growth rate yet, recorded at 157.0 parts per billion. And I go on, this was supposed to be the easy part in mitigating climate change. Sad times ahead. Yeah, methane, the whole idea is that if we cap a few wells, maybe change our eating habits, don't eat as much meat, change some of our farming methods, we can control our own methane release. And if we do enough of that, then methane won't rise, and this is a greenhouse gas that has a very short-lived half-life, and so it would naturally come out of the atmosphere, and because it's such a powerful greenhouse gas, that would give us some sort of cooling effect in the near term, that would give us some time to deal with a much longer lived and more catastrophic rise in CO2 levels. So that's the plan, right? The plan is, let's do this sort of short-term silver bullet of lowering methane. The problem is that plan isn't working. And in fact, the opposite seems to be going on. We are having this sort of meteoric rise in methane levels that really should be shocking us, because they lay to waste all of these other plans for controlling global growth, global heat in the near future. So let me just show you this graph a little bit closer and talk about what it is. So this is the annual mean growth rate. So it's a little complicated to understand those words. So essentially, when we look at methane over the long run, we have the sort of up and down month over month, and it goes through sort of this wavy pattern and generally goes up on a wavy scale. And that's confusing because these sort of waves, they come and go seasonally, but we don't get a sense for a long-term average. So in order to get around that, if we sort of average the amount of methane over a period of 12 months, then we can talk about sort of the annual mean amount of methane. And because we have this sort of sliding window of 12 months at a time, we can sort of keep track of 12 months, 12 months, 12 months, and so on. And that would be the annual mean growth rate. But the problem is that there's something else going on here, and that's this half-life of methane being 110 months. So what happens is that every single month, however much methane we happen to have in the atmosphere, a certain amount of it just sort of naturally goes away. It leaves the atmosphere due to oxidation, and the result of this oxidation is carbon dioxide and water vapor. We lose most of the methane down low in the troposphere, and once it gets through there into the stratosphere, it lasts much, much longer. So tropospheric methane, they say about 9.6 years is the typical half-life. One of the problems is that because we're increasing our methane, this oxidation also requires hydroxyl radicals. And we don't have as many of these radicals in the atmosphere as we used to, because they're all, well, they're interacting with the methane that's going up there. And so what seems to be happening is that we're actually having more of this methane get up to the stratospheric levels, which means that it's going to stick around even longer, right? So we should expect this half-life of 9.6 years to be increasing with time, which is very bad news. I use 110 months just for convenience. This is maybe a little bit of a rough approximation. So, because we are actually getting a rise in methane, but we have this degradation in the amount because of its oxidation, it means we have to be putting even more into the atmosphere than the raw numbers tell us. And that's what I wanted to capture, is what is the real amount of methane that's going into the atmosphere. And what we see is this huge spike here on the right-hand side of it, starting about 2018, middle part there. And I don't know. I can't point to a source because I haven't seen a good study on this, but you can certainly guess that it might be Siberian permafrost melting, or it might be the East Siberian Arctic shelf there releasing some of the methane caltrates. So it can be a lot of different things, right? And I don't know. And I don't want to speculate on that. I just want to present this data and let you see it. So where does this come from? Where does this graph come from? Well, it comes from data, right? And this data that I used itself comes straight from this source right here, the Global Monitoring Laboratory of NOAA. So here is that sort of curvy line I was alluding to earlier. And here is sort of where they straighten it out, and you see this line right here. And this graph right here is just keeping track of the current amount of methane in parts per billion, sort of averaged over a 12-month period. But it doesn't tell us how much we're adding. It just tells us our current state. And I wanted to get from this to how much methane we are adding to the atmosphere. And in order to do that, I needed to go to this raw data. Again, that's right down here, the globally averaged marine surface monthly mean data. And if you go through this, it will tell you how they get the data, that there's certain uncertainties in it, that it gets recalibrated, usually a few times after it's originally posted, that some of the values might change a little and so on. But it starts in 1983, this sort of global estimate of methane. And the first estimate was 1,626 parts per billion. And it continues on now until the latest one that just came out, which was for June of 2021, which is 1,888.8 parts per billion. Now, it takes them a few months just to be able to do these computations and simulations and these estimates and to collect all the data from all the different stations all over the planet to do this analysis. So we don't have the September numbers here, and we won't have September until early next year, for example. So we always have to be looking back a few months in this. So what I wanted to do was to use this data right here in order to, together with sort of knowing that there is this 110-month half-life, in order to really get a sense for how much methane is going into the atmosphere. And that's where I created a spreadsheet to help. So let me just show you that spreadsheet here. So you might need to zoom in or something in order to see it clearly, but across the top, the headings are year, month, and the average. So these are the three columns that are sort of key from the data. I didn't use the average uncertainty or the trend uncertainty in anything I was doing. And the first thing I wanted to do was get a sort of a trailing 12 months to get this 12-month average, much like the actual graph that you saw from NOAA. And you see that right here. I'm simply adding together the previous 12 months. I'm taking the average of the previous 12 months to get these numbers here. Now, because I'm not doing a curve fit, and I'm actually just coming up with these numbers as a 12-month trailing average, they are pretty steadily going up the whole time. We are not getting any bumps or bounces. It's just none of this sort of wiggle that you saw in that graph. It's just sort of averages together and goes straight up. And it goes up, we see all the way up to the most recent value is 1887.3. Now, how do you take account for the fact that methane has this half-life? Well, the way you do it is best illustrated by an example. Let me just show you this very first month here. This is June of 1984. We had 1,638.7 parts per billion methane. Now, when we get to July, how much of that methane is left? Well, 110 months will lose half of it. So the formula that you learn, well, you learn about second quarter calculus, is that if you have a half-life of 110 months, then the amount you lose in 1 month will be 1/2 raised to the power 1 divided by 110. And that's exactly what I use up in this formula. I multiply this 1638.7 by that number 1/2 raised to the power 1 over 110, which means the amount of methane that is left over that hasn't been oxidized after that month is 1,628 parts per billion. And so this whole column then is simply taking the value that was sort of diagonally up to the left and multiplying that by this weird 1/2 to that power. And I do that all the way down. All right, so now what do we do? Well, what happens next is that we look at the trailing 12 months, which is 1639.6, and we say, but only 1,628.4 of that is left over from what I actually had last month, which means I had to add 11.3 parts per billion to this to get to what I actually have. So what we have, it degrades. Measure again, the difference has to be how much we added, right? Then what we have, that degrades because of the half-life, and then again, we measure what we have, and the difference is how much was added. And so I'm able to have this column, the new CH4 that we added each month, and that's what goes right here in this column, how much new CH4 we added each month. Now, that's not quite done yet because once again, we're looking at an annual mean, right? So once again, we want to say, well, over any 12-month period, how much did I add? Well, these numbers are raw amounts that I added. So that amount will accumulate over a 12-month period. So I'm not taking an average this time, right? I'm taking a sum. So this 137 number right here is the sum of these values, these 12 values. So I had to wait another 12 months before I could start doing sort of the annual mean, right, to see how much was added. So over this year, I added 137, and I can simply keep track of these numbers then, how much I added in the previous 12 months, all the way down here. So that's what I get. And you can just follow this down, or you can watch these numbers that we're adding, sort of go through the 130s and 140s and creep up to the 150s. And then in this last month, this very last month we just went through, the number is 157 parts per billion added. And if we just sort of look at how fast this is accelerating here, this is sort of mind-blowing how fast we are now adding methane to the atmosphere, new, fresh, clean methane, in order to keep up with these numbers. So we've never had a month with 157, an annualized year with 157 parts per billion before, and now we do. And to me, that is big news. That is big, scary news. And I just wanted to make sure that we understood where this graph was coming from so that we can see just how critical, how absolutely overwhelming our methane problem is right now, that this is the singular crisis going on. Yes, it'd be great to stop the CO2. Let's kill the fossil fuel industries. That's all good. And whether it's 2030 or 2050, net zero, or whatever they're saying, it's not going to happen tomorrow. So in the meantime, we need to mitigate methane, and that's what's not happening. We are not mitigating methane. Methane is absolutely skyrocketing here. It is going off the charts, and that's what's got me worried, honestly. So, okay, everyone, that's what I wanted to share with you today. Yeah, it's tough times. It's going to be tougher, and I am just going to hang in there, hopefully do these a little bit more often. Sometimes it gets a little bit overwhelming to try and figure out exactly what you want to talk about. There are so many things going on right now, and they are all so sad. So, all right, everyone, Elliot Jacobson. See you later.